Okay, we're given this flat piece of tin that measures 10 inches by 15 inches. We want to make a box with no top on it. How we're going to do this is we're going to cut a little square out of each corner. Now these have to be kind of the same height. Like each one of these, I'm going to say is X on each side. Because we want this box to fit together nicely, however much comes out of one corner has to be equal on each of the corners so that when we fold this up, it's going to make a nice little box. All right, so we want to figure out how to get the largest volume. How do we get that greatest volume? So one thing we want to do is be able to represent our volume. So volume, we can think of this as length times width times height. All right, so it may take a little bit of visualizing on here, but if we kind of take these corners and we fold them up, the height of this box is going to be however much we cut out, say, of this portion, right? If this is cut out, the yellow, we fold this corner up, that's going to be like one side of the box, and it's going to have a height of however much we cut out right here. So I'm going to start with the height, and I'm going to say that's just going to be represented with X. Now the width and the length are a little bit interchangeable, which one you want to treat as which. If I say coming all the way across here, I want to make that the length on this box. But it's not going to go all the way across there. It was 15 to go all the way across, because remember, we cut out part of it. We cut out part of that 15. So we want to figure out what are we left with on the inside here. Well, we started with 15 all the way across, but we cut out an X on this side and an X on this side. So I'm going to say the length is actually 15 minus 2 of those X's. And we can do something very similar on this, going all the way across what I'm going to refer to as the width of this box, that it was 10 all the way across when it was nice flat, but we cut this part out to fold up this side. And we cut this part out to fold up this side, so that entire width going in between here wasn't quite 10. It would be 10 minus 2 of those X's. All right, a little bit confusing, I know. Take some visualizing, get a piece of paper out, cut some corners out, fold stuff up. Hopefully you can make sense of it. All right, so the volume, I'm going to go ahead and distribute, multiply this out a little bit. So the volume, and I'm going to call it V of X, is going to be, I'm going to go first, outer, inner, last of these first two binomials. So in this case, I'm going to get 150. Outer, we get 30x, inner, 20x, and then last plus 4x squared. Combine some like terms together on the inside here. We get 150 minus 50x plus 4x squared. Still have that x on the outside, so I'm going to go ahead and bring that x to the inside. So I'm going to have to distribute to do so. So I'm going to say 150x minus 50x squareds plus 4x cubes. So all this is just representing our volume function. To optimize this, to find the very largest volume possible, we want to find a critical number. To do that, what I want to do is take the derivative of our volume function and figure out when it equals 0. So the derivative here, just using the power rule, is going to be 150 minus 100x plus 12x squared. Okay, so we've got the derivative. We still have a quadratic for our derivative, but that's okay. With this, let's go ahead and see when is that going to equal 0. So I'm going to set it equal to 0, and I'm going to rearrange the right-hand side. So I'm going to put it in descending order by moving the 12x squared up front, minus 100x, plus 150 I'm going to put at the end. All right, we have this quadratic. I think we can factor out at least a 2 from each one of these terms. That'll leave us with, what, 6x squared plus 50x, sorry, minus 50x plus 75. Now, I don't think we're going to be able to factor this one nicely, unfortunately, what's still in our parentheses. So what I'm going to do next is go ahead, and it is a quadratic, so I'm going to say A is going to be 6, B is going to be negative 50, and C is going to be 75. And I'm going to solve this down by using the quadratic formula, which may not be your favorite, but it is what it is, as they say. So this is going to be, our solutions are going to be represented by negative of B plus or minus the square root of B squared minus 4 times A times C all over 2A. Okay, so a little bit of reducing down from here. It's really just following our order of operations. Negative 50 squared is 2,500. And then, let me see, 4 times 6 times 75 is negative 1,800. So 50 plus or minus the square root of 700, all divided by 12. Now, really, this is two different solutions, right? That's what that plus and minus means. So this is going to indicate that we have 50 plus the square root of 700, which doesn't reduce down nicely, the square root of 700, that is, and x is equal to 50 minus the square root of 700, all divided by 12. Let's get an approximation for this. All right, for the top one, where we're adding, I got this to be about approximately 6.375. And on the bottom, I got this to be about 1.958. When I did my computation beforehand, I may have approximated. The square root of 700 was about 26.5 as I went through this, so I may have rounded too early for what I should have done. So these may be slightly different than what you get if you put that in your calculator at the very end, which you should be doing instead of rounding early. But we can still get the point across, even though I may have rounded a little bit early. Are these both solutions or not? All right, let's think about this. How much should you cut from each corner of the box of this tin, from each corner of the tin, so the resulting box has the greatest volume? Well, let's think if both of these could be solutions or not. All right, let's think if we first of all cut 1.958 inches from each corner. So if I cut away, we had 10 at the beginning. If I cut away 1.9 from this side, that'd be okay. Same thing where we started with 15 on the other side. The longer side isn't going to be a problem, either one of them. All right, so that would be a good solution. So I'm saying, oops, I'm going to use my eraser on accident. This is 1.958-ish. That is a good solution. So I'm keeping that one. But let's think about 6.375. Can I cut 6 inches off from each corner? So if I start with 10 going all the way across here, and I take 6 off this side, and I take 6 off this side as I cut out my corners, that's a little bit of a problem, right? You can't take 12 total away, or else, we only had 10 to begin with, so that doesn't work as far as the dimensions of our tin went. So we kind of have to throw that out just on principle that that's not allowed, right? If we were actually making this box, you couldn't take 12, a little over 12, out of each one of those corners and still end up with a box. All right, so that's going to be our solution, the 1.958 or whatever you got, as maybe a little bit better approximation than what I got. All right, but I hope this helps out. It's usually the setup that is the most troubling on these, not so much the approximating at the end. So hope this helps out as you're working on these problems. Good luck.